In the last video, we found the center of mass of some point objects. Now we're going to find the center of mass of a solid object. We're going to start out by looking at the center of mass of a uniform rod. Why a uniform rod? Because I already know the answer. Its center of mass is going to be at the center of the rod. Our formula for point objects is this: the sum of each mass multiplied by its x-coordinate divided by the total mass. And instead of point objects, we have a solid object. We pick some little tiny infinitesimal chunk of mass. We call that dm, some little tiny part of the whole rod. It's so small, we can treat it like a point mass. So we're going to multiply each dm times its location. And if I situate my rod like this on the coordinate system, the location of this dm is just x. And I'm going to add up all the contributions from every little dm. And what does that become when we have a solid object? An integral. And I'm integrating over the whole length of the rod. I'm adding up all the dm's that make up the length of the rod. And in the numerator, I get the integral of dm, which is just m, the total mass of the rod. Now this is just like what we did when we were finding rotational inertias. We integrated over all the little dm's. So let's take a quick look. When we have a one-dimensional object, a two-dimensional object, or a three-dimensional object, we can use dm as follows. All of our objects are going to have some total mass, whether it's one-dimensional, two-dimensional, or three-dimensional. For a one-dimensional object, we only have one dimension. We have length. For a two-dimensional object, we have area. And for a three-dimensional object, volume. So if our object has uniform density, a one-dimensional object is just going to be the mass divided by the length. The total mass divided by the total length will give us the density if it's uniform. The same density throughout the whole object. For a two-dimensional object, we would get the total mass over the area. And for a three-dimensional object, we would divide the mass by the volume. And we use different symbols, if you remember. For density, the mass density of a one-dimensional object is lambda, and lambda has units of kilograms per meter. For a two-dimensional object, we use sigma, kilograms per meter squared, and we use rho for the density for a three-dimensional object, kilograms per meter cubed. So we're just doing a one-dimensional object, a rod, and I've already said I've got the x center of mass is going to be equal to x times dm, and I'm integrating from 0 to L, and I'm dividing by the integral 0 to L dm. And what is dm? dm is the mass of this little red chunk here. And how would I find the mass of a little piece of my rod? What if I handed you a long rope and I said, tell me the mass of this little section in the middle, but you can't cut my rope? What would you do? You'd weigh the whole rope, find the mass, you'd measure the length, you'd find the density, and you'd multiply that by the length of my little section of interest. That's what we're going to do here. If this is x, the location of dm along the rod is x, then its length is dx. So my dm is just some length multiplied by the mass density. Now, if my rod is a one-dimensional object along the x-axis, ds is just dx. If I had a curved rod, ds could be an arc length. That's why I put ds. It's a little more general. But in this case, I have a straight rod lying on the x-axis. Just use dx in this case. Now I can take this and plug it in for dm in my equation here. Now I always ask myself when I get to this point, is lambda constant? If the answer is yes, it comes out of the integral. If the answer is no, then we're usually given some kind of function for lambda, and we would just plug that function in, and it changes the integral a little bit, but we would go ahead and integrate at that point. So is lambda constant? In this case, yes it is. It's a uniform rod. Lambda comes out. And I've got an x squared over 2 evaluated from 0 to L. And I've got an x evaluated from 0 to L. And what is lambda? Lambda is just the total mass over the total length, if it's uniform density. So I'm not canceling my lambdas here because I want to show you that my denominator is going to equal m, the total mass of my rod. And you see that that's the case. So what we found was that the center of mass of a uniform rod is at the center of the rod.